Hi everyone. We're nearing the end of chapter 18. In this video, I really wanted to discuss laboratory applications and how this stuff starts to show up whenever we are doing experiments. So, putting it all together in the lab, in the laboratories, what we really want to do is be able to find a value for delta H and a value for delta S experimentally. But it turns out that while we can measure delta H experimentally, that's calorimetry, we worked on that, it's very hard to experimentally measure the entropy of a system. And so the only way for us to be able to measure the entropy of a system experimentally, well, not the only way, but the easiest way, is that we use the equilibrium constant. And so an experimental plan looks something like measure the equilibrium constant at multiple temperatures. We use those measured equilibrium constants to calculate the Gibbs free energy at each temperature. And then we graphically determine delta H and delta S using that delta G information. And this is actually what you are going to do in your second law of thermodynamics experiment. So, we've got to put this all together. So, in this data, the equilibrium constant was measured at several different temperatures. Now, remember how we measured the equilibrium constant? What we had to do was we know that for this case, K is equal to the concentration of HI squared over the concentration of H2 times the concentration of I2. And so what we had to do was we had to measure the concentration of each product and each reactant at several different temperatures, plug those into the K expression, and calculate our equilibrium constants. And so in order to find delta H and delta S, the first thing that we are going to have to do is find delta G. And delta G is equal to minus RT ln K. And so I'm going to do one example here, and then I'm going to just plug in and report out the values. And so for this first data point, we have that delta G is going to be equal to minus 8.314 joules per Kelvin times mole times 150 Kelvin times the natural log. And I'm out of space. Let's move over. So delta G standard is equal to minus 8.314 joules per Kelvin times mole times 150 Kelvin times the natural log of 1.4 times 10 to the minus 6. And if I type that into my calculator, I get that delta G is 1.681 times 10 to the fourth joules per mole. So what I would do is the same process for each point. And if I do that, I get this data out. And so now I know delta G at a bunch of temperatures, but ultimately I want to find delta H and delta S. And so this is where we use the relationship that delta G equals delta H minus T delta S. And in the fashion of the semester, this equation is a lot like y equals mx plus b. It's just rearranged and out of order. And so what that means is that we can make a graph. Oops, and I even got this wrong. I got this way wacky. X times m. Because what we have, the data that we have, is we have the temperature, which is the variable that we are controlling on the x-axis, and delta G, which is the variable that we are measuring on the y-axis. And if I graph this, I get a line equals y equals mx plus b. And the slope of this line is going to be equal to negative delta s. And the intercept of this line is going to be equal to delta h. So whenever I graph this data, I get the fit of the line as y equals negative 225.49x plus 50626. And so we remember that delta G equals delta H minus T delta S. And so delta H should map onto my intercept, which is going to be 50626. Now I need some units. The intercept is the y-intercept, and so those should have the same units as our y-axis, which is joules per mole. And then my delta S should equal negative of my slope, which is negative 225.49. Now my slope has units, and my units of my slope are the units of the y value divided by the units of the x value, which is joules per mole divided by Kelvin. Or delta S is 225.49 joules per Kelvin times mole. And so in your experiment in the lab, you are going to create data just like this, and you're going to use the relationship that this delta G equals delta H minus T delta S maps onto the equation of the line. And to remind you of how that mapping works and to make sure that we're all on the same page with that, we have delta G is my y value equals negative delta S as my slope times times T, which is my x value, plus delta H is my intercept. Okay, I hope that helps. I hope that makes some sense about how we can take these equations and map and how they look like a line and how we can extract our values out of them.